Okay, good morning. So let's get started from what we were doing last time. So today we will first complete some parts of the discussion that was incomplete last time, and then we will discuss about how the different types of scheduling algorithms that we had discussed, how they can be extended to handle task dependencies. Actually, if you remember, we had said that first we are going to discuss very simple situations where the tasks are independent uniprocessor, and then we are slowly bringing in the reality where we are going to discuss first about the handling the dependencies among tasks. Then we will see what if we use multiprocessors and distributed systems, because nowadays, as you know, multiprocessors and distributed systems are becoming the norm. Uniprocessors are slowly becoming obsolete. So with that motivation, let's proceed today. First we will complete the discussions that we could not complete last time, and from then we will go to handling task dependencies. So towards the end of last class, we are discussing about priority inversions under the priority ceiling protocol, the different types of inversions that can occur. So if you recall what we are discussing, we are discussing that priority ceiling protocol reduces the total duration for inversions. The highest locker protocol, we had remarked that it's not used because there are too much of inversions in this and tasks can miss their deadline. But even though the PCP, the ceiling protocol, it reduces the priority inversions, but we had seen that they still suffer from three main types of inversions. What are they? Anybody remembers? What are the three types of inversions that tasks can suffer in the priority ceiling protocol? Right. So looks like you remember. So one is the direct inversion, inheritance related inversion, and then the avoidance related inversion. And we are trying to compute these inversions for a arbitrary situation. So that was what we were doing last time. We had done some examples and also had given you one exercise to do. Now let's do one or two more exercise so that we understand the issues here in priority ceiling protocol, because this is the one actually used in the commercial operating systems, and when you implement an application in a real time using a real time operating system, this is the one which you would be using. So let's look at this situation. 6 tasks are there and 3 resources, and this is their sharing the resource requirement and the duration for which they need the resource. And then if you remember, we are preparing 3 types of tables. One was for the direct inversion, and the other for inheritance related inversion, and one for the avoidance inversion. So what about this one? The direct inversion for T1, it suffers direct inversion due to which tasks? I mean, I can write that table also. So maybe it's a good idea to write the table so that everybody understands that. So we have 6 tasks: T1, T2, T3, T4, T5, T6, T1, T2, T3, T4, T5, T6. Now, how much direct inversion does T1 suffer on account of any other task? Let us first identify that by looking at the diagram. Let me just also give the title of the table as the direct inversion table. So does okay, please tell me how much inversion does T1 suffer from other tasks? It suffers from T2, is it? For what duration? 2, right? As I can see, T1 suffers, it can suffer inversion due to T2 for 2 millisecond. And any other task? T4. So, T4 how much? What is the duration? Can't see. Okay, so let me just write 5 millisecond. So, now let us look at the diagram again. Please look at what are the inversion that T2 suffers on account of the other tasks, and then we will populate this table. So, let us wait for the table to come up here. Yeah, sorry, the diagram to come up. The diagram has come up here. So, T1 suffers inversion due to R1 and R2, right, and the tasks involved are T2 and T4. T2 causes inversion for 2 millisecond and T4 for 5, that is what you had said. What about T2? T2 due to T6 for 8, and okay, let me just write down T2 for T6 for 8 millisecond. Okay. Now, let us look at the diagram again. Let us identify the inversions due to T3. Will T3 suffer any direct inversion? No. What about T4? No. What about T5? No. T6? No. So, only T1 and T2 suffer direct inversions. So, those two only we have populated, and the rest we do not write anything, those are 0. Is everybody comfortable with this? Okay. Now, let us try to find out the inheritance related inversion. I will use the same table, maybe with a different pen. I will just write down near that. So, let us find out the inheritance related inversion. Does T1 suffer any inheritance related inversion? Yes. What is the definition of inheritance related inversion? Anybody would like to answer? What do you mean by inheritance related? I mean, how does that occur? How does inheritance related inversion occur?
A lower priority task gets the
a lower priority task has the resource, and then
intermediate task will block the higher priority task.
Okay, another task is
Intermediate task.
waiting for the resource, is it? And then the priority of the task holding the resource goes up by the inheritance clause of the priority ceiling protocol.
So, the intermediate tasks which do not require the resource are getting blocked.
Yeah, no, that is okay. Inheritance. Okay, so that's the inheritance related inversion. The once the intermediate tasks are getting blocked. So here for T1 to get blocked, one task with at least as much priority as T1 should be requested the resource, and T1 itself cannot wait for itself, isn't it? It can undergo inversion. So T1 can't undergo inheritance related inversion, isn't it? Yes or no? Okay. So T1 does not undergo any inheritance related inversion. What about T2? Look at the diagram on the screen. Will T2 undergo an inheritance related inversion? Yes. Okay. So it will undergo inheritance related inversion due to T4, right? So T4 is holding the resource, T1 is waiting, and T2 can undergo an inheritance inversion for 5 millisecond. And any other one? Any other cases it can undergo inversion? No. What about T3? T3 will undergo inversion due to T4 and T6. And what about T4? T4 due to T6. And what about T5? T5 also due to T6. So let me just write that down. So, you said that T1 does not undergo any inversion and T2 undergoes inversion on account of T4, and that is for phi, and T3 undergoes inversion on account of T4 and T6 for 5 and 8, and T4 undergoes inversion due to T6 for 8, and T5 can undergo inversion, inheritance inversion on account of T6 for 8. Does everybody agree with these figures? Okay. Now, let us look at the avoidance inversion. So, please observe the diagram again, the figure, the task figure, and let us try to find out the avoidance inversion. Okay. So, let the yeah, it has come up. So, will T1 undergo any avoidance inversion? Please think over what is avoidance inversion. I mean, how does avoidance inversion occur? Yes, anybody would like to answer? How does avoidance inversion occur? Yes, anybody remembers how does avoidance inversion occur?
Sir, a task is not granted immediate access to a resource.
Okay.
Even though, like,
Okay. So, this occurs due to the ceiling value. So, there is a system ceiling, remember, there is a current system ceiling, and whenever a task acquires a resource, the system ceiling is set equal to the ceiling of that resource, right, and whenever a task requests the another resource, the task's priority is checked against the current system ceiling. Only if its priority is greater than the current system ceiling, or it is the task which is set the ceiling, which last acquired the resource due to which the ceiling was set. Under these conditions, the resource is granted. If the task's priority is less than the system ceiling and it is not the task which last set the ceiling, resource will be refused even if the resource is available. And this was, we had seen that this is to prevent deadlocks. So, let us look at the figure again, the task figure, and try to find out the avoidance inversions. Will T1 undergo avoidance inversion?
yes.
How will T1 undergo avoidance inversion? Just tell me the situation. So, some of you are saying yes. Let's hear how T1 will undergo avoidance inversion.
So, like, suppose T6 is accessing the resource R3.
T6 is accessing. So, R3's ceiling value will be set, system ceiling, no problem, this will be lower than T1. That is not the situation. Sorry, that is not the situation. How will T1 undergo avoidance inversion?
T2 tries to acquire R1.
Okay, it can, okay, since no one is answering, let me just refresh your memory. See, when T4 acquires R2, the ceiling will be set is equal to the priority of T1, because that is the ceiling of R2, isn't it? And now let us say T1 is requesting for R1, it won't be granted. Otherwise, there can be deadlock situation, isn't it? So, just listen to the situation. T4 is already holding R2, and that time T1 requests R1, it will be refused. Yes.
When T4 is accessing R2, the ceiling value is set to the priority order of T1.
T1,
So
yes.
the ceiling priority, system ceiling is set by the task T1.
No, it is set by T4. On account of T4 holding the resource, the ceiling has been set. So, T4 will be allowed to access another resource, not T1, not T1. But if, what about T1 requesting R2, will that be avoidance inversion? No, it won't be, it is a direct inversion. So, T1 requesting R1, so for T4, T1 can undergo avoidance inversion for how much duration? 5. Will it undergo avoidance inversion due to any other task? Yes, due to T2. Due to T2, because just look at the situation, T2 is already holding R1 and T1 might be requesting R2, and in that situation it will undergo an inversion for 2 millisecond. This is avoidance inversion. What about T2? Will it undergo avoidance inversion? Okay, it can undergo avoidance inversion on account of T4, because T4 might be holding the resource R2 and T2's request for R1 will be rejected, or I mean it has to wait, because the ceiling value is set to 1, right. So, the duration will be 5. What about any other? Yeah, on account of T6. So, T6 might be holding R3 and T2 might be requesting R1, and in that case it will undergo for 8 millisecond. What about T3? Will it undergo avoidance inversion? No, it does not need any resource. So, it cannot undergo an avoidance inversion because it will not request for any resource, is not it? Only when the request for resource is denied due to the ceiling value, it will undergo inversion. What about T4? Will it undergo inversion due to T1? No, because T1 is already higher priority and T4 does not need any other resource. But what about? No, but what about for other tasks? It won't undergo for T1, but will T4 undergo inversion due to any other task?
So due to T6.
Yes, it will undergo avoidance inversion due to T6, because as T6 acquires R3, the system ceiling will be set to that of T2, right, to be equal to 2, and T4 if it requests R2 will be denied and it has to wait for 8 millisecond maximum. What about T5? It will not undergo inversion because it does not need resource. What about T6? No, T6 is the lowest priority, a lowest priority task does not undergo any inversion. So, let me just write down your observations. So, you said that T1 undergoes inversion on account of T4 and T2, on account of T4 for 5 and on account of T2 for 2. Okay, let me use a different color, just using the blue. So, the blue is for inheritance inversion and the red is for avoidance inversion, and T2 undergoes avoidance inversion on account of T4 and T6. So, T4 it will undergo for 5 and T6 for 8, and T3 does not undergo any avoidance inversion, does not need any resource, and T4 will undergo on account of T6 for 8 and T5 does not undergo any avoidance inversion. So, now a task we had seen can undergo at most one inversion, and T1 the maximum duration, we just look through the row and find that 5 is the maximum duration for which it can undergo inversion, T2 for 8, T3 for 8, T4 for 8, T5 for 8, T6 is 0, right. Okay. So, let us proceed from here. Is this clear? How do we calculate the inversions? Now, let us look at the, I think there is one more exercise here, much more complicated, that one with huge resource requirements, large number of resource requirements for different tasks. But if you have understood how we computed for the previous exercise, you will be able to do it. Should we work it out here? I mean, would you like to work it out here, or do you think that it is okay? Anybody would have difficulty working out, then we can discuss, otherwise we can just skip and give you it as an exercise. What do you think? Should we try it out here? Okay, let me not write it at least, let me just ask you, because that is quick. So, what about T1, will it undergo direct inversion? What about direct inversion for T1? T1 won't undergo direct inversion due to T3. See T1, see direct inversion, they are sharing the same resource. So, due to T5 and T6, T1 can undergo direct inversion. What about? Okay, yeah, right. So, direct inversion, T1 can undergo direct inversion due to T3 for 4 and on account of T4 for T5 for 5 and on account of T6 for 8, right. What about T2? On account of T3 and T5. What about T3? On account of T6. On account of T2 it won't undergo inversion because this is a higher priority task. T3 will undergo inversion due to T6 and also due to T5 on account of R1 sharing, right. So, due to T5 and T6. T4 will not undergo any direct inversion, it does not need any resource. What about T5? It can't undergo any direct inversion, it is not sharing resource with any lower priority task. Similar is T6. Now, what about inheritance inversion? Will T1 undergo inheritance related inversion? No, it is the highest priority and we can't have a situation another task is waiting, isn't it? Another task with higher priority waiting. What about T2? It will undergo due to T5 and also T3 and also T6. What about T3? Will it undergo inheritance inversion? Due to T5, yes. And also, no, will it undergo T6? Yes. T1 is sharing with T6. So, on account of both T5 and T6 can undergo inheritance inversion. What about T4? It will undergo due to both T5 and T6. What about T5? Will it undergo inheritance inversion? Yes, due to T6. And let us look at the avoidance inversion. Will T1 undergo avoidance inversion? Yes or no? Yes, it will undergo inversion. So, which tasks? Yeah, it due to it can have inversion due on account of T3, on account of T5 and on account of T6, right. So, once they acquire a resource, it cannot even see once T3 acquires R3 and T1's request for R2 will be rejected, right. Similarly, for T5 acquires R2, T1's request for R3 will be rejected. Similar is with T6, right. Now, what about T3? Will it undergo avoidance inversion? On account of which tasks? On account of T5, you would always have to look for the lower priority tasks. So, on account of T5 acquiring R2 or T5 acquiring R1, right. Any of these cases it will undergo an inversion, and also for T6 acquiring R3, right. Okay, let us proceed from here. Looks like you are comfortable determining the different types of inversions under the priority ceiling protocol. Now, once we have found out the longest duration for which a task can undergo priority inversion, that is the highest entry in the corresponding row of the task. So, that is Bi. So, we will have to modify the Liu and Lehoczky condition. We add Bi also here. because that is the inversion, maximum inversion it can undergo, and then if still the task meets its deadline, then the task will be schedulable. If Bi is too much, then it may not be schedulable. Now, we have seen that how priority ceiling protocol can be extended, or the analysis of the priority ceiling protocol can be done to check whether a set of tasks will meet their deadline or miss their deadline based on their resource sharing requirement. But what about a dynamic priority system like EDF? Can PCP, a protocol such as a priority ceiling protocol, be used for dynamic priority system? See, if we have to use a protocol like priority ceiling protocol, we will have to compute the priority ceiling value for every resource, and we know that the virtual priority of task keeps on changing, and we have to update the ceiling for each resource and also the current system ceiling. And if we try to do that, it will incur unacceptably high processing overhead, and we can't use resource sharing under dynamic priority systems is extremely difficult, and this is one of the main reason why EDF is not used. We had seen some examples where the rate monotonic algorithm is used. Later as we proceed, we will see more and more examples where the rate monotonic algorithm is used for task scheduling, even though it is less proficient than EDF. Now, let us just compare the different resource sharing protocol. Recollect that we had said that the basic inheritance scheme, the priority inheritance protocol, is simplest, requires minimal support from the OS, only we need to reset the priority value of the task when another task is waiting for the resource. That is the only requirement, and it could overcome the unbounded priority inversion problem, but tasks can suffer from chain blocking and deadlocks. These are severe problems, and we had discussed about the highest locker protocol requires moderate support, where we set ceiling for resources, keep track of all ceilings of all resources, and then as a task acquires a resource, its priority is changed to that of the ceiling priority, and then after it releases the resource, the priority is reset. It solves the chain blocking and deadlock problems, but the intermediate priority tasks can suffer from inheritance related inversions, and since the task is raised to a high value, the tasks suffer from inheritance related inversions frequently, and this can lead to deadline misses because there are frequent inversions. And we had seen an improvement over the HLP form of priority ceiling protocol, overcomes the shortcomings of priority inheritance protocol. It is free from deadlocks and chain blocking, and also it incurs lower inheritance related inversion as compared to the priority ceiling protocol. The main reason for why it incurs low inheritance inversion is that the priority of a task does not change when it acquires the resource. So, intermediate priority tasks will not get affected, unless of course a higher priority task is waiting for the resource. Now, let me just ask a few questions, simple questions, just to check whether you are following what we are doing. Now, just listen to this statement. When a set of real time tasks share a certain critical resource using the priority ceiling protocol, the highest priority task does not suffer any inversions. Do you agree with this? Yes or no? Okay, it suffers direct inversion, but any other types of inversion? It can also suffer from avoidance inversion. It may not suffer from inheritance inversions. Now, let us look at this statement. Under priority ceiling protocol, a task not requiring any resource may still undergo priority inversion for some duration. Do you think this is a correct statement?
Inheritance.
Okay. It can still undergo inheritance related inversion. What about avoidance inversion? No, it won't. Only inheritance related inversion it can still undergo. Now, this is just a thought question. So, why is it that the priority ceiling protocol is not a greedy algorithm, whereas inheritance protocol is called as a greedy algorithm? What do you think? Can you give an example or something why ceiling protocol is not a greedy algorithm?
So the problems we worked out, sir.
Yes.
The situations where avoidance related inversions are occurring. Sir, from there we can argue that it is not a greedy algorithm, PCT.
Okay. So, anybody has any other idea? See, he gave an answer, I will just tell that answer. But what about any other answer? Anybody would like to give any other answer?
As we are not increasing the priority of task retrieval.
No, see, this is a question of whether it is a greedy or not greedy algorithm. It is not nothing to do with priority. It is the way the algorithm operates. Can we call it as a greedy algorithm? If we cannot call it a greedy algorithm, just give an example to justify why it is not greedy. Okay, not very hard to think actually. See, a task will be blocked even though the resource that it is requiring is available. No one is using that resource, but still the task will be blocked. If it was a greedy algorithm, it would have, if the resource is available and its priority is okay, etc., then just give it the resource. But here the task is having higher priority than the current one that is running, and the resource is available, but still the task will be blocked. That is due to the avoidance related, to overcome the avoidance inversions, right, like he was answering. So, it is not a greedy algorithm because when the resource is available, it still does not grant. Okay, so just think about it. Now, why under dynamic priority protocol supporting resource sharing among real time tasks difficult? What problems would occur if we are using a dynamic priority protocol such as a EDF, earliest deadline first, and then we want the tasks to share critical resources? What kind of problem will occur?
Inheritance related.
Suddenly the priority will change.
Yes.
And then then we don't know. Suppose we have assigned a lower priority.
Exactly. So, there will be too many inversions because implementing a protocol to minimize the inversion is very difficult because the ceiling value itself changes dynamically. The task priorities change and the ceiling values change, and we can't think of a protocol. I mean, nobody has thought of a protocol which can be used to reduce the inversions. So, it is unusable when the tasks have to share critical resources. Okay. Now, let us proceed from that point.
So, in dynamic system isn't there any resource sharing at all?
It is very difficult. See, if the chances, if the system is loaded, right. See, if a task rarely executes, then we can think that, see, that task may not cause inversions to other tasks. Now, let us say that task runs frequently and it also using critical resources, it can cause inversions to other tasks under EDF, right. And if the deadline is close, it is millisecond or something rather than minutes, then it would become unusable. The tasks will undergo inversions for long duration and there can be deadline misses, and if the deadline, the consequence of deadline misses are not acceptable, then, which is true for most hard real time systems, then we cannot use it, right. Okay, let us proceed from that point. So, now let us try to bring in this complicacy. So far we assume that the tasks are independent, which is far from the truth. in most practical situations. In practical situations, tasks do have dependencies. Unless something completes, another task cannot start, and we need to modify the existing algorithms. Fortunately, not very difficult. It is not too much of a complication. Let us see how to handle that. First, let us look at our table driven algorithm, because we had looked at the table driven ones as the clock driven algorithm as an example, and then we had looked at the event driven algorithms, the RMA and EDF. So, first let us look at the table driven algorithm, what to do here, and then we will look at the RMA and EDF. In table driven algorithm is a simple algorithm to extend the table driven algorithm to handle task dependencies. We arrange the tasks in increasing order of the deadlines. After having done that, we scan the tasks from the rightmost end and find yet to be scheduled task whose successors have been scheduled, and then we schedule it as late as possible such that the task does not miss its deadline. We continue doing this while there are tasks yet to be scheduled. So, that is, the list is exhausted, and then after finding this schedule, we move all the tasks forward as much as possible. We will just see that with the help of an example. So, this is the example. We have 5 tasks here, and this is the execution time. For T1 it is 2 millisecond and the deadline is 8, T2 it is 5 and 25, and this is the precedence relationship between the different tasks. Now, let us see how do we apply the algorithm. So, first we arrange the tasks in ascending order of the deadlines. If we observe that task characteristics, we will see that T4 has a longer deadline than T5. So, this is the order that is worked out here. T1 and T2 has a longer deadline than T3. So, T1, T3, T2, T5, T4, if we arrange them in terms of their task deadlines. Now, here we have taken T4 and 50 is its deadline. So, we have scheduled it here. It runs for 10 millisecond its execution time. So, up to 40, and T5 can run from 40 to 33. T2's deadline is 25. So, it can run from 25 to 20, 5 millisecond is its execution time, and then T3 can be taken up at 20 and it can take 6 milliseconds. So, from up to 14 to 20, and T1's deadline is 8 and it takes 2 milliseconds to run. So, it can start at 6 and the worst case, right, these are the worst case start times for the tasks, and still none of the tasks miss their deadlines. That is what we have worked out here. And the step 3 is move all these forward. So, this as T1 we move it to 0 to 2, and then from 2 to 8 T3 has come, and 8 to 13 T2 has come. So, we have moved everything forward, and this is the final schedule for the table driven scheduler.
Here there is no role in the period of the taxes.
See as if you remember, see the question somebody is asking is that what about the period of the tasks, aren't we consider that? See, if you remember what we were discussing in the table driven scheduling is that we compute the schedule for one major cycle and then keep on repeating that. So, this is for one major cycle we have computed the schedule, and then we will keep on repeating this.
But we are changing the phase of that initial phase when we are moving it forward.
No, see here, okay, let me just again clarify. See, he is talking about phase, but see here we did not specify any phase. So, the tasks are assumed to arise at 0 millisecond, right. So, as long as it is not scheduled before 0, then we are doing all right. If any task is having a non-zero phasing, then of course we can't move it before that. So, that is the complication we will have to consider when tasks have non-zero phasing, but here we have implicitly assumed tasks have zero phasing. Is that okay? Okay, fine. So,
And the periods are also not considered. Means all the tasks arrive at the same time.
no, see, since somebody else is also asking the question, let me just revisit that problem that we are showing. See here, in many cases where these task dependencies exist, right, like this tree we have seen here, shown here. So, T4 depends on the results of T2 and T3. So, first T1 needs to be executed, then T2 and T3, then possibly T5 or T4 or T4 and T5, that is the order that is permissible. But these tasks they occur together, right. So, they keep on repeating, no, unless T1 completes, T2 cannot complete. So, this way they will keep on repeating. So, the period for this all of them is same, maybe 200 for each one. So, every 200 millisecond T1 will occur once, T2 will occur once, T3 will occur once, right. So, all of them have same period. And of course, if you say that what if they have different periods, then it is not very meaningful, no, because see T1 has, let us say, occurred 2 times and T3 1 time only, then T3 should succeed which one, right, that question comes. So, this whenever there are precedence relationships, the tasks occur together the same period, and that is equal to the LCM that we have assumed and we have just computed for one such cycle, major cycle. Is that okay? Okay, fine. Okay, now let us see. We saw that for cyclic schedulers, it is not very difficult to handle task dependencies. Simple algorithm, just found out their worst case completion times, and based on that we said that what is the earliest, what is the latest by which it should start, and then we for each of them we did that and then moved them forward, right, simple thing. But now let us see how do we extend the EDF and RMA to handle task dependencies. Precedence constraints can be handled with again simple modifications. The modification is as follows. We will take some example and illustrate. We will have to modify the task parameters actually. We should not enable a task. See, so far we are saying that a task is enabled, can start executing any time after its phase. If it has a non-zero phase, we can't start execution before its phase, right. So, after the phase the task becomes ready, it is executed. But what you are saying here is that even though the tasks has some phase, we can't really make the task ready. We will keep the task pending, will not make it ready, will not enable it until all its predecessors complete execution. Simple thing, because see it is needing results from the predecessors, or in other words let me just say that the task cannot start until its predecessors cannot complete. So, we will change its ready time, which may be more than its phase. So, keep it pending, we do not bring it to the ready queue until its predecessors complete. And then also we need to do another thing. The scheduler needs to check the tasks waiting after completing the task every task completes, because after a task completes it might happen that the task that is waiting for this to complete, right, the duration for which it is complete might have been over. So, this is the simple modification that we have to do. Now, let us look at that with some examples. First we will look at RMA. Earlier so far we had independent tasks T1, T2 etc., they are given to the RMA scheduler. But now we will have precedence relations between tasks, we will modify the task parameters and then we will give it to the scheduler. So, the modification that we will do for the rate monotonic algorithm or the rate monotonic scheduler is that the ready time of a task j, ready time of a task j after modification is written star, ready time of a task j should be greater than equal to the maximum of the ready time of this task, that is the phase of this, and that for all its predecessors. Ri star is the all its predecessors, and then we will also change their priorities. Let us see how we do that with the help of an example. Let us assume this kind of a task precedence, that T1, T2 take 1 and 2 millisecond here to execute, and T2 has a phase of 6 millisecond. T2 has a phase of 6 millisecond. T3 requires 3 millisecond to execute. T4 takes 1 millisecond to execute, and T6 takes 5 millisecond to execute, and T5 takes 5 millisecond to execute, and T6 has a phase of 5. Only these two tasks are non-zero phase, right. Now, their deadlines are also given, and see all their periods are the same, 200. So, T1 has a deadline 10, T2 15, T3 25, T4 40, T5 65, and T6 70. So, these are the phases for these tasks we have written here. T6 has 5 and these have 0, 6, R2 is 6, right, R2 is 6. Now, if we find the maximum of R1 and R3, so that is 0, is not it? So, this is equal to 0. Now, for R4 it will be maximum of this, and this 3, right, which is equal to 6, is not it? So, make it equal to 6. Now, what about T6? It will be having a phase of 5. So, it will be maximum of 0 and 5. See, we are modifying the ready times. Okay, we are doing for this one. So, this will be maximum of 6 and 0, which is equal to 6. And for T6, it will be maximum of 0 and 5, right, maximum 0 and 5, which is 5. So, we will modify the ready times, simple thing to do, so that the task precedents are honored. But just modifying the ready times are not enough, because even if the task becomes ready slightly late, but if what if T1's priority is becoming less, because they are all will having equal priorities here, is not it? See, they all have equal periods. So, we need to give different priorities to them, so that they enable the predecessor to complete before the successor can be taken execution. So, the predecessor should have a higher priority, is not it? Is not it? So, that is what we will do here. We will just keep on assigning T1 is 1, 2, 3, 4, 5, 6.
Yes, we will take deadline to complete or rate.
No, if we take not really deadline, we are just looking at their precedence, because unless a successor does not complete, a predecessor does not complete, the successor, if it starts, then it will block it if it has a higher priority.
So for tasks at the same level, we look at the deadline.
Yeah, just because they are all same period, their priority would have all been same, and with same priority this will not work. Tasks can miss their deadline. So, what we are trying to do is assign them priority, so that a predecessor will not get blocked on account of a successor, or in other words, this will enable them to follow this sequence of execution, the sequence in which their there in this task graph, we are just giving them the same priority. But possibly what we could have done, see between T3 and T4 they are at the same level in the tree. So, we have the flexibility which priority to, I mean how to distinguish between these two in the priority.
Can they be given the same priority?
Same priority, then we will have to check if both of them will meet their deadline in the worst situation.
T3 should be there more than because its deadline is much
Exactly. So, what we see is whichever tasks deadline is lower, we give that higher priority. If we give them equal priority, then we have to check whether both of them will complete by
In
that time.
case of, since it is a modified RMA,
Yes.
so we don't consider for the deadline as a criteria for allocating.
No, no. See, the priorities are all in a rate monotonic algorithm given based on the frequency or the period. But what we are saying is that here they should have all got the same priority, but we are trying to give them in different levels of priority because we want the predecessor to succeed, I mean the predecessor to complete before the successor can start, because what if the successor starts off and the predecessor has not completed and some predecessor, then that will get blocked, isn't it, and then this chain cannot will be violated. Simple thing, just think about it.
But since they are at the same level in the precedence graph, so they can be given the same time.
No, that argument is not valid. See, what he is saying is that whether tasks in the same precedence level can be given the same priority. No, that argument is not valid, because you have to also consider the deadline. No, what if T4 keeps on executing and T3 cannot complete before T4 completes? T3 might miss its deadline, isn't it? So, what we say is that between T3 and T4, who has the nearest deadline, and give it the higher priority. Now, let us see how to modify EDF. Similar thing we will have to do here, only slightly complicated, slightly more complicated here. Here for the ready time of a task, we look at the ready time of that same task and also all its predecessors ready time plus the execution time. And we will also have to change the deadlines of the tasks, because the scheduling is done based on the deadlines, and this is the way we have to compute the deadline, and we will just take some example in the next class and see how a task with precedence relation, a task set with precedence relations can be scheduled under EDF successfully by modifying their ready time and their deadlines, right. So, we will stop here and meet next class, carry on from this point. Okay, thank you.